Hi, I'm Nimrod from BDN Automotive, and now you're watching the fourth episode of BDN Combustion Analysis tutorial video series. In today's episode, we're going to talk about the basics of data acquisition systems, some interesting applications where the BDN CA6 could be very useful for you. But first of all, let's start with the on-road mapping, which is very important because no dyno is needed to map your car anymore. Let's start with it. To understand why we actually do not need a dyno anymore to map our race car, we need to look into the correlation between torque, Imap and Imap. As you can see on the left side and the right side of the screen, the left side is a torque and horsepower curve from the dyno. The right side is the Imap plotted from the BDN CA6 combustion analyzer. The torque and the Imap curve pretty much looks the same. The reason of this is behind the theory, basically. Because BMEP is brake mean effective pressure equals to indicated mean effective pressure plus the frictions. If you want to calculate torque, this is also correlating to BMEP cylinder volume 2 pi plus NC. NC is the number of revolutions needed for a combustion cycle, which is basically, if you're using a 4-stroke engine, this number is 2. So the reason why the torque and the Imap curve looks pretty much the same is that basically they are directly correlating to each other. So if you are, for example, running in a static set point with your engine on a dyno or on the street or whatever, the frictions are not going to change. If the engine's temperature is not changing too much, frictions are going to be pretty much the same. So if you measure an Imap increase on the street, that means that your torque is increased as well. Let's move on to the next topic, which is data acquisition and signal processing. When you do any kind of data acquisition, there are 3 very important things to know. First of all, the sensor's range. I'm currently not talking about the range in pressure or bars or whatever, but I'm talking about the sensor's output voltage. Our commonly used sensors are outputting 0 to 5 volts, but there are some other sensors which are outputting -10 to 10 or 0 to 3.3 volts. Second thing, the sensor's resolution. Here again, I'm not talking about anything in pressure or anything what you actually measure, but the bitwise resolution. Our ADC is 12-bit ADC, which means that there are 4,096 points, different points, what you can actually differentiate. The third one is sample rate, but for the sample rate, let's move on to the next slide. Let's say that the engine is running at 6,000 RPM, which means that the rotational frequency is 100 Hertz. If you would like to record every single degree of crank angle, obviously, then it means 36 kilohertz of sampling rate. Let's move on to the picture on the right side. The red curve here, this is the signal of a knocking cycle. If we are recording with a 1 degree resolution, it means that we are capturing every 10th point on this graph, and we're getting the black curve. This is not so useful for us because we're cutting off basically the whole range of the knock. Okay, so then let's say that we would like to record on 0.5 degrees. This is the blue one. We're kind of capturing something, but if we're not recording here and there, but in the middle, then we again cutting off some peaks. So rule of thumb again, when you're doing combustion analysis, usually you record 0.1 degree accuracy, which means that at 6,000 RPM, you at least need 360 kilohertz sampling rate. To calculate the required sampling rate by the data acquisition system, first of all, you need to know what the signal is looking like, what you would like to capture. As I earlier talked about the knock signal, you need to know how often do you need to sample to capture everything what you need to capture. Secondly, Nyquist criteria. Usually everyone forgets about this one. When you have a sensor with a, let's say, 0 to 70 kilohertz frequency range, then you at least need the sample by the twice of this. So in this case, 140 kilohertz. Some more pretty interesting applications where the BDNC ASICs could be extremely useful are, for example, the very initial phase of cold start calibration, mainly for OEMs. In this phase, you really need to know how much fuel is injected for each cycle. And if you have a misfire or a partial misfire or something like this, then obviously you're not going to pass emissions. Secondly, and at the end of this video series, we would like to talk about our future, because currently we are developing a real-time combustion control system. What is it actually? So let's imagine that you can replace an engineer by an artificial intelligence, because now you know how a combustion analysis system works. Obviously you know how to tune an ECM, but you still need to sit there, read the data, and based on your knowledge, you need to tune the car. Let's say that you replace it with an artificial intelligence, and basically the car will map itself on the go. On this screen, you see an Imap plot versus ignition advance and AFR. Green means high performance, and red means low Imap, aka low torque. Our system is basically moving around this table and looking for the optimum performance. So let's say that the ECU set point is currently here, which is 18.95 bars Imap. The system will try to go to this point where the Imap is 19.88 bar. However, on the go there is a limit, which is the knock. So it cannot go through the knock zone because obviously our engine is going to blow up. So what the system will do instead of that is it will search for the optimum performance below the line, which will be here in the corner, and it's 19.39 bars Imap, which means 5% direct increase in performance. Stay tuned, because this system will be out soon. Make sure you subscribe to our newsletter in the link below to get all the relevant info and updates, and of course, the next sessions of the BDN tutorial videos. Get the most out of your engines, and let's win races together.